Diffusion models have recently emerged as a dominant approach in visual generation tasks. However, the lengthy denoising chains and the computationally intensive noise estimation networks hinder their applicability in low latency and resource-limited environments. Previous research has endeavored to address these limitations in a decoupled manner, utilizing either advanced samplers or efficient model quantization techniques. In this study, we uncovered that quantization-induced noise disrupts direction estimation at each sampling steps, further distorting the precise direction estimations of high-order samplers when solving the sampling equations through discretized numerical methods, thereby altering the optimal sampling trajectory. Our motivation is illustrated in Figure 2, which intuitively explains the role of noise estimation in inverse diffusion sampling. Subfigure A shows that the estimated noise in a first-order sampler essentially corresponds to the tangent direction of the sampling trajectory. Subfigure B demonstrates that a second-order sampler first computes an intermediate point and evaluates the first-order direction at that point, then combines it with the first-order correction at the interval starting point to obtain a more accurate joint sampling direction. Subfigure C illustrates how quantization noise leads to drift in the sampling trajectory by perturbing the direction estimation at each step. Subfigure D explains our core motivation. We aim to obtain a probability flow that is more linear and more robust to noise by aligning the high-order trajectory from for precision computation with the quantized first-order trajectory. Specifically, the core mechanism of our sampling-aware quantization method is mixed-order trajectory alignment, which is detailed in section 4.1, where we also demonstrate its application using DPM solver as an example. To accommodate the different quantization bit width requirements, we propose sampling-aware post-training quantization in section 4.2 and the sampling quantization dual-aware LoRa in section 4.1. Furthermore, in section 4.4, we present a solution for adapting our method to more general samplers, such as PLM sampler adaptation methods. Finally, we evaluate the effectiveness of the proposed method on multiple benchmarks in section 5, including class conditional generation tasks, unconditional tasks, and text-guided image generations. A more detailed analysis and additional visual results are provided in appendix. Thanks for your time.